All right. All right. So I'm now recording the session. All right. So we are going to begin. All right. Now, the first thing I want us to look at is, so under epicyclic gears, right, we are either going to make use of spur gears or bevel gears, right? So I want us to look at how, or I want us to look at when we get to use spur gears and when we get to use um, bevel gears, right? Right. Now, as far as spur gears, right, if you have to, or if we have to design a gear system, right, if you have to design a gear system such that the design of that gear system, you must design gears that, when fitted with the shafts of those gears must be such that it is parallel to each other, right? So if you are required to design a system, a gear system, where the gears have to be fitted such that the shafts are parallel to each other, right? So if you look here, this we can take as a spur gear meshing with this spur gear, right? So this we can regard as a pinion, this we can regard as a gear wheel, right? Now, as far as gears, the smallest gear in the system we call a pinion. A pinion meaning it is a small gear, right? And then the gear that it meshes with, if larger in diameter or PCD, right, we're going to refer to that gear as the gear wheel, right? So this here represents the pinion being the smaller gear, and this would represent a gear wheel being the larger gear, right? So again, if we have to design a gear system where in that system the shafts are going to be fitted onto the gears such that they are parallel to each other, right? If you look at these shafts, the two shafts are parallel to each other, right? So if you have to design a system where the shafts have to be parallel to each other, then we make use of what? Of spur gears, right? But if you design a system where the shafts essentially have to be perpendicular to each other, right? We then instead make use of what? Of bevel gears, right? So this here represents the shafts that are being fitted onto the bevel gears, right? And then a bevel gear is somewhat cone shaped, right? If you look at this here, this is somewhat cone shaped. So this here represents a schematic of a bevel gear, right? If you look at the major difference between a bevel gear and a spur gear, right? A bevel gear can mesh with gears on this side as well as on that side, right? The bevel gear can mesh with gears on either side of it, right? So you'd have teeth ground onto it on this side, right? So you can mesh with gears on this side as well as on this side, right? Now, the major difference between bevel gears and what is this uh, 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 um, and spur gears is that with spur gears, right, if you have a pinion meshing with a gear wheel, right, so if you have two spur gears meshing, right, when they rotate, if one is rotating clockwise, the other one is definitely going to rotate anti-clockwise, right? So spur gears are such that when they mesh, right, when they mesh with the outside true circumference, right? So by outside true circumference, I am referring to if you have a gear that has teeth ground onto it on the outside, right? Remember, gears, you are able to ground teeth onto them on the outside as well as the inside, right? A spur gear that has teeth ground onto it on the inside is normally referred to as a ring gear or an what is this? Or an analysis gear, right? So if a spur gear, right, is such that it has teeth ground onto it on the outside through circumference, and it meshes with the gear that has teeth ground onto it on the outside through circumference. So essentially, if you have two spur gears, right, and they are meshing with the outside through circumference, right, those gears tend to go in opposite direction, So if this one is going clockwise, that's going to go anti-clockwise, right? It's the same case if, say, this gear was on this side, right? The fact that they are meshing with the outside true circumference, they are going to go in different directions, right? Whereas with bevel gears, right? With bevel gears, that is not the case, right? With bevel gears, now, first of all, right, because the configuration of gears, right, is many, right? We are only going to look at the configuration of bevel gears from this perspective. So from this perspective, I mean, you're always going to have one bevel gear in the middle. You're always going to have one on this side and one on this side, right? So by that, I mean, right, let's refer to this one, right? So this is an epicyclic gear system made of bevel gears, right? So when I say we are always going to have, or we are always going to look at bevel gears from this perspective being you're always going to have a gear in the middle, one on the left hand side, one on the right hand side. This is what I mean here, right? If you look at gears D, C, and E, right, you have one bevel gear in the middle, right, and it has two gears meshing with it on either side of it, right? You are always, so that's what I mean by we are always going to look at bevel gears or bevel gear systems from this perspective, right? But that I'll expand on later, right? So the major difference between a spur gear and a bevel gear is that I've already explained the spur gear, that if the two meshing gears are meshing with the outside true circumference, then those two gears will go in different directions. Whereas with bevel gears, the direction depends on taking into account that the perspective will always be like this one, right? The direction of the gears in mesh will depend on which side of the bevel gear, right, are the gears meshing, right? So for instance, if you look at the gear in the middle here, right? If you look at the gear in the middle, if you are looking at a bevel gear that is meshing with the gear on the left of this gear, right? Those two gears tend to go in the same direction, right? So even if, say, there wasn't, say, we didn't have this, right? Say we didn't have that gear, right? You only had gear A and B, right? Because gear A is meshing with B on the left-hand side of B, right? These two gears will tend to go in the same direction, right? But now, if you're looking at a case where you have a gear meshing with B or the middle gear on the right hand side of it, then these two tend to go in different directions. Right now, I'm going to, there we go, this picture. Right, can everyone see this picture?
Yes, we can.
Yes, sir.
Right. Uh, let's call this. So let's call this A. Can you see the lettering? Can you guys see this?
Yeah.
Yes, sir.
Is that a differential?
Yes.
Okay.
But don't mind what this is. Just focus on gears A, B, and C. Right? If you look at gears A, B, and C, right? Essentially, you have the same configuration as the schematic I've just shown you, right? On the schematic I showed you, you had a gear in the middle, right? And the gear in the middle was meshing with two gears on either side of it. Do we see that here? Hello?
Yes, yes.
Right. Now, I want you to use your own imagination because this is a picture, it's not a GIF, right? Think about what would happen to gear B, right? Think about what would happen or how gear B would rotate if gear A was rotating in this direction, right? Say gear A is going clockwise, right? So it is rotating like that. It is going clockwise. So if gear A is going clockwise, meaning it's going in that direction, right? If you look at it from a linear motion perspective, let's say it is going in this direction. So it is essentially pushing gear B, right? If this is rotating clockwise, right? I want you to think about it. How is this going to rotate?
In the same direction,
Clockwise.
as well.
Clockwise, right?
Correct. Yeah.
So this is exactly what I mean, that if you have gears meshing, right, with the middle gear on the left-hand side, right, or if gears mesh such that they have this configuration, right, they tend to go in the same direction, right? And then now I want you to think about, so this is going clockwise, right? Now, if gear B is going clockwise, right, gear B is going clockwise, and if you look at it from a linear perspective, if it is going clockwise, right, it is essentially going in this direction from a linear perspective, right? So again, if gear B is going clockwise, it is essentially going to push gear C, right? So if this is going clockwise, how is gear C going to rotate?
Anti-clockwise.
Anti-clockwise, right? So you see what I mean when I say, when looking at bevel gears from this perspective, which we'll always look at bevel gears from this perspective, right? This gear and this gear will tend to go in the same direction, whereas the gears meshing on this side, right, will tend to go in opposite directions. Are we clear here? Are we clear?
Okay.
Yeah. Good stuff.
Right. So let us go now. If we are clear, right, let's consider this bevel gear, right? Consider gears A, B, and C, right? If you look at gear A and gear B, right, based on what we just covered just now, if you look at gear A and B, will gear A and B go in the same direction or opposite directions?
Definitely. Same direction. Sorry, that's the output. So it's not the input, right? Should I consider the input?
Don't mind the shafts, right? Just look at gear A and B, right? Will A and B go in the same direction or go in opposite directions?
So they will go in the same.
Same direction. Remember, if you look at this configuration, right, it is exactly the same as this one, right? Yeah. So here, we just proved that if this is going clockwise, that's going to go clockwise. So meaning these gears will tend to go in the same direction, right? And then we also proved that if this is going clockwise, this will tend to go anti-clockwise, meaning these ones go in opposite directions. So now my question is, you are looking at this case of bevel gears, right? We are looking at gears A, B, and C. Would gear A and gear B go in the same direction or opposite directions?
Same direction.
Same direction, yes. So if this is going clockwise, that's definitely also going clockwise. So these two will go in the same direction, right? And then what about B and C? Same direction or opposite direction?
Opposite direction.
Say again?
We'll go opposite directions.
Exactly, right? Opposite directions. Now, if you look at gear E now, right? Can you guys see this? If you look at gear E and D, will those two go in the same direction or opposite direction?
Same direction.
There we go. Yes. But it seems like I'm talking to one person here. Where are the people?
No, we follow
same direction, sir.
Right. Same direction. Yes. Right. So that is how we look at bevel gears. Right. Now, if there was another gear, right, meshing with gear D on this side, would that gear and gear D go in the same direction or opposite directions?
Opposite.
Opposite.
There we go. Yeah, perfect. Right. So that is how we look at bevel gears. Right. So similarly to this case. Right.
So
Yes.
Oh, sorry. Just a quick question. I'd like to know just the previous picture that you showed us. The other one. If E and D was not fixed, would we ever get an example where E and D would not be fixed inside of that specific gear, and it's an independent gear, always going to be fixed inside of the gear.
I've never really come across such a case.
Because it looks to me like D is it's fixed. It's part of the gear, but E
Part of
seems
which
like
gear? As in part
so
of the
B and D.
Epicyclic.
Yeah. So B and D looks like it's one, but A and E could be two. It could be it could go independent, or you could actually make it.
I see.
Go
Right.
at the same.
Okay. I think I get what you're trying to ask me. Right. Yes, you are right. Gear B and D are compounded together. Right. So whichever direction that this goes, and whatever the rotational frequency of this is, this will have the same rotational frequency. Right. Now,
exactly.
That I would say would depend on which epicyclic gear system of bevel gears you are looking at, right? For this particular epicyclic gear system made of bevel gears, that will not happen, right? Now, the reason for that is under bevel gears, we get two types of systems or two types of epicyclic gear systems, right? You get an epicyclic gear system made of bevel gears, right? And then we get this one here, which is a humpage epicyclic gear system, right? Now, for a humpage epicyclic gear system in particular, right? Any and all gears and arms or any and all components we take as being part of the what? Of the epicyclic gear system, right? So because of that, this gear, right? So in this case, this gear is gear D, right? This gear will always be compounded with gear D will always be compounded with gear B, right? Why? Because that is just how a humpage epicyclic gear system is designed to work. Right? So again, for a humpage epicyclic gear system, which is this one, right? This will always be the case. Are we clear?
Yes.
Right? So like I said, you get two types under bevel gears, you get two types of epicyclic gear systems, right? I've already mentioned this one. This is a humpage epicyclic gear system, right? Where we treat all components involved in the system as being part of the epicyclic gear system, right? Now, what that means is, now with epicyclic gears, what we tend to do is turbulate our information, right? Do you guys remember this? Remember that the table that has two fixed conditions, right? First condition being you fix the arm and rotate the annulus by 1 revolution clockwise. And then the second condition is you multiply the first condition by X and then add Y. Do you remember that part?
Yes.
Right. With epicyclic gear system, we tend to turbulate our information. So when I say any and all component for a humpage epicyclic gear system, right? All the components we take as being part of the epicyclic gear system, meaning that any and all components will be turbulated. Are we clear?
Quick. So where would you deploy a humpage gear system? I mean, you have various types of gear systems, but where would you specifically? I mean, I know automobile, but for which specific reason would you deploy a humpage gear system?
So a humpage gear system, I don't think they use them anymore, but they were primarily used in lathe machines. They were primarily used in lathe machines, right? Now, if you look at, I'll show you the page on where to read on humpage gears, right? But the one system I can think of right now is a lathe machine, right? Which in 2024 they are actually not being used anymore. Right? I think, in fact, that's one of the reasons why, as far as exams, you are hardly ever asked on bevel gears, right? Because
see.
under bevel gears, they'll either have to ask you this case, right, or this case, which we'll get to just now, right? But because this system is hardly or is no longer in use, right, in industry, that's why I think, if I think about it, right, I would say this is actually part of the old syllabus, because Humpage gear systems, right, as primarily they were used in what is this, in lathe machines, right, but they're no longer used in lathe machines anymore.
Yeah.
Right. Any more questions? No questions. Right. Now, like I said, you get two types of, under bevel gears, you get two types of epicyclic gear systems. Right. I've already covered this one. The other one is called an epicyclic gear system made of bevel gears. Right. So you get a Humpage epicyclic gear system, and then you get an epicyclic gear system made of bevel gears. Right. So the way we treat this one, right? The way we treat this one is we only look at the gears that essentially surround the what? The arm. So the arm here is this arm YY, right? So the gears that are surrounding the arm YY, those are the gears we take as being part of the epicyclic gear system. So those gears would be gears D, C, and E, right? Now gear B, because it is compounded with gear C, right, we inadvertently consider it as being part of the epicyclic gear system as well, because whatever rotational frequency this is rotating at, as well as whatever direction that this is rotating, this will rotate in the same direction as C, as well as at the same speed, right? But gear A, right? Gear A is not necessarily part of the epicyclic gear system, right? Or of the epicyclic gear system made of bevel gears, right? Its sole purpose is for us to what? To fit the input shaft, right? So for whatever reason, for this system, right, to make the gear ratios or gear reductions work, right, the input shaft is fitted onto the external gear. So the gear A here would be regarded as an external gear, right? And this external gear would always be fitted with what? With the input shaft. Right? So again, you get two types. Under bevel gears, you get two types of what is this? Epicyclic gear systems. One is the Humpage epicyclic gear system, where we treat any and all components as being part of the epicyclic gear system. Hence, we tabulate any and all components. Right? Whereas with a epicyclic gear system made of bevel gears, right, we only take into consideration, for instance, in this case, gear D, C, and E as being part of, well, of course, and the arm as being part of the epicyclic gear system. Hence, when tabulating your information, you would include the arm YY, gear D, gear C, and gear E, right? So gear B, you would
Excuse me, sir.
from a sense. Yes?
Can you hear me?
Yes.
Okay, sorry, sir. It's just I was having problems with my microphone.
Sure.
I just wanted to ask, just to clarify, if gear D rotates clockwise, gear C will rotate anti-clockwise if we're looking at from the direction of the shaft going inward to the center of this diagram.
No. If this one is rotating clockwise, this will also rotate clockwise.
Okay, so by the points they meet in the corner, they won't be going towards each other. They're going away from each other.
Yes.
Okay, yes, that's all I wanted to know. Thank you, sis.
Okay. Okay.
Maybe draw arrows.
Arrows.
Yeah,
For the clockwise, just maybe upwards for D and to the left for C.
I don't understand what you need me to do. Arrows to do what exactly?
Just to indicate the clockwise direction. Maybe people can't see that. D goes up and C maybe goes to the left.
I'm lost. So
Okay,
you
no,
want
it's fine.
you want me? So
Just
you
points
mean
that
from a linear motion perspective?
Correct, yeah.
Oh, so if this, from a linear perspective, if this is going in that direction, right, that is us assuming clockwise. So one of the reasons why I actually don't want to do that is because remember in the first condition, right, because this is not a typical epicyclic gear system, we would have to choose one of these gears to be what? To be our analyst. The analyst being the one that's going to rotate clockwise. So depending on which gear we choose as an analyst, that is also going to affect our directions. So meaning, for instance, if say you choose this one as your analyst, it means this is going clockwise. So if this is going clockwise, that's going anti-clockwise, that's going anti-clockwise as well. The most important thing here is understanding the relationship between the two gears as far as direction of rotation. Right? So as in knowing if this is going clockwise, this is going in the same direction. And if this is going clockwise, this is going in the opposite direction.
Okay.
Are we clear? Hello?
Yeah, no, understood.
Right. What was I saying? I don't remember what I was saying now. What was the last thing I said before the question?
I think you're describing the part where you're actually explaining the bevel gear, the system, and the Hamish gear system.
Right. So I just finished explaining the humpage gear system. Now with the epicyclic gear made of bevel gears, right, you would only turbulate gear D, C, and E as well as the arm, right? Now gear B, right, you would also turbulate. Why? Because essentially C and B go in the same direction, right? So if say this is the gear we choose to be as our analyst, right? From condition one, the analyst rotates by 1 revolution clockwise. So if this is 1 revolution clockwise, that's also 1 revolution clockwise, right? Another thing, the way we use our external gear, right? The way we use our external gear, right, is by calculating or is by using the relationship between A and B, between these two gears, right? Because remember, with the tabulation of your information, you have conditions 1, 2, and then the third condition, right? The third condition, that is where you get to answer the question that you've been asked, right? In answering that question or to complete the third condition, you need 3 things, right? You need what you are looking for and then 2 other assumptions, right? Now, bearing that in mind, for an epicyclic gear system made of bevel gears, the way we treat the external gear, right, is for us to be able to get the rotational frequency of this gear B, right? If you look at gear A, it is fitted with the input shaft. The input shaft is rotating at 300, right? So if the input shaft is rotating at 300, it means gear A is rotating at 300. We have the number of teeth of gear A. We also have the number of teeth of gear B, right? So we can use the relationship of these two meshing gears to calculate what? The rotational frequency of B. That rotational frequency we are going to use in our third conditions. In our third condition, right? Remember what you need to complete the third condition, what you're looking for, and 2 other assumptions. So as far as the two other assumptions, once you've calculated the rotational frequency of B, that you will use as one of the two assumptions you need to complete the third condition. Right? Remember that if you have the rotational frequency of this, you inadvertently have the rotational frequency of gear C. Right? So essentially, we use this external gear to calculate the rotational frequency of this gear B, right? Which we'll then use as one of the two assumptions we need to complete the third, or is the third condition, right? But that I will expand on as far as conditions. Are we clear here as far as the two types of systems we get under bevel gears?
I think it's good. The moment
Yes,
you
sir.
give examples, it's together.
Sorry?
I'm saying I think it's good. Maybe when we do examples with the conditions, it will become much clearer.
Right. All right. Okay. So as far as where and how we get to use Spur gears and where we get to use bevel gears, that is pretty much it. All right. So now I want us to look at an example here. Okay. Okay, let's start with the basic one. This was in one of your videos, right?
Yeah, that's correct.
Okay, maybe let me do this as the second one. First, I want us to look at a typical epicyclic gear system case. Okay, maybe this one. Right, let's look at this one. Let's look at this one. Yes. All right, so let us look at this case. Right, so for this one, we are only going to look at 1.1. Right, for now. We're going to look at 1.1. Right.
I'm having some intermittent connection issues on my side, so hopefully it's not a problem.
Second.
I'm just having some intermittent connection issues on my side, so hopefully it's not a problem.
So if you miss any part of this lesson, you can catch up on YouTube. I will be posting this lesson on YouTube for guys who couldn't attend the lesson. No?
Yeah, for sure. Thanks.
Right. Now, people must pay attention because what we're about to do now is of utmost importance that you understand. Right. I'm going to show you the easiest way you can approach problems based on epicyclic gears. Are we clear here?
Yes.
Yes.
Yeah.
Right. So I wanted us to look at a typical epicyclic gear system. Right. So by typical, I mean now a typical epicyclic gear system is one that has an annulus. Remember, I mentioned earlier that a spur gear can either have a teeth ground onto it on the outside through circumference or the inside through circumference, right? And proceeded in saying the ones that have teeth ground onto them on the inside through circumference we regard as the ring gear or annulus gear. So annulus and ring gear is one and the same thing, right? So a typical epicyclic gear system is one that has the following, what is this, components. So annulus or ring gear. Matching with the annulus, you have the planetary gear. And matching with the planetary gear, you then would have the sun gear. Right? Now, the gear meshing with the annulus, which we regard as the planetary gear, right? The PCD, the pitch cycle diameter of this gear, right, will always be such that if you have a planetary gear here, right, the PCD, so from here to there, right, so the distance, the measurement from here to there will always be such that it is equal to the measurement from here to there, right? So whether or not this is here or not, right, whether you have another planetary gear here or not, right, the distance from here to there, so this diameter, right, will be equal to one of the pinion. Are we clear here?
Yes.
Right, that is important to note. Why? Because sometimes it could happen that you're looking at a typical epicyclic gear system, right? So one that has an annulus, planetary gear, sun gear, right? But you do not necessarily have the number of teeth of all the gears, right? So for instance, if say you have the number of teeth of the planetary gear as well as the number of teeth of the sun gear, and you do not have, or you haven't been given the number of teeth of the annulus, right? How would you go about calculating the number of teeth of the annulus, right? By using this schematic here, right? You know that if this is a, what is this? If this is a pinion, right, then this represents the PCD of the pinion. So to get the PCD of the annulus, it would be the PCD of the pinion plus the PCD of the sun. And now you know that this measurement here will always be such that it is equal to what? The PCD of the pinion. So essentially, the PCD of the annulus is equal to what? PCD of the pinion plus the PCD of the sun plus the PCD of the pinion. All right. So essentially, this is what you'd have. Right. To get the PCD of the annulus, it is equal to what? It is equal to the PCD of the pinion plus the PCD of the sun plus the PCD of the pinion again. Are we clear here?
Yes.
Yeah.
Yes.
Right. Now, what is the PCD equal to? PCD is equal to module times number of teeth. Right. So expressing the PCD in terms of module and number of teeth, this will become module times the number of teeth of the annulus is equal to the module. Now, take note that this is exactly equal to that. So essentially, you can rewrite this as being equal to 2 times the PCD of the pinion plus the PCD of the sun gear. Agreed?
Yeah.
Right.
Yes.
Now expressing this in terms of module and number of teeth. So this becomes 2 times the module times the number of teeth of the pinion plus the module times the number of teeth of the sun gear. Right. Now for gears, right, for gears to be able to mesh, their modules have to be the same, right? So mathematically, if the modules of the gears are the same, it means this is essentially going to cancel out, and you're left with the number of teeth of the annulus is equal to 2 times the number of teeth of the planetary gear plus number of teeth of the sun, right? So if you're missing any one of these gears' teeth, you can simply use this formula here to get them, right? So for instance, if you're missing the number of teeth of A, and you have the number of teeth of the planetary gear as well as the number of teeth of the sun, you can simply use this to calculate what? The number of teeth of the annulus. Similarly, if you have the number of teeth of the annulus as well as the number of teeth of the sun, but you're missing this, again, you use this formula. Make TP the subject of the formula, and you get your number of teeth. Are we clear?
Yeah.
Yep.
So we are clear.
Yes, you are.
Right. Right. So when I refer to a typical epicyclic gear system, it is one that has a ring gear, planetary gear, and a sun gear, and of course the arm. Right. And then you get atypical epicyclic gear systems, right? Like one, like this one. Where's this thing? Where's this thing? There. Right, like this one, where you don't necessarily have an analyst, right? You just have a simple gear train, right, that has an arm, right? So without this arm, this is not an epicyclic gear system. What makes this an epicyclic gear system essentially is the arm here, right? So in such a case, because there is no analyst, right, or ring gear, then you would have to choose one gear to be your analyst. Now, for such cases, right, for such cases, I would advise that you, in fact, I would insist on you choosing the biggest gear in the system to be your what? To be your analyst. Are we clear?
Okay.
Right. Right. Now let us look at this example. Right. Now, as mentioned, when looking at problems based on epicyclic gears, you have to tabulate your information. Right? Your information has to be tabulated. Right? Information has to be tabulated. Right? Right. Now, in your table of information, right, you have two fixed conditions. By two fixed conditions, I mean the first two conditions, right, are not dependent on anything. Those two conditions are the same always, whether it's morning, afternoon, or evening. Right? Those two conditions do not change. Right? So the first condition being you are going to fix the arm and rotate the annulus by 1 revolution clockwise. Right? So we write this condition just like this here. So you fix the arm, right, and you write down what the arm has been labeled as, and you rotate the annulus by, now we use shorthand for by 1 revolution clockwise. So instead of writing that whole story, right, we write that in shorthand by simply saying by +1 rev, right? So this here stands for 1 revolution clockwise, right? So the 1 revolution and then clockwise is the plus, right? So for gears, clockwise we take as positive, anti-clockwise we take as negative, right? Now, in completing the first condition, right, you only need one thing. You need the number of teeth of the gears, right? In order to be able to complete the first condition, you just need the number of teeth of the gears. If you have the number of teeth of the gears, that is essentially everything you need to complete the first condition, right? So essentially, the first condition, you can even complete without even having read the statement or questions, right? If it's such that, say, you have the problem statement and you've been given the diagram, right? And from the diagram, you can get the number of teeth of all the gears, right? Then all you do is you write down the number of teeth, right, at the top of each column. And from there, you complete your first and second condition, right? It's only from the third condition that you need to know the information embedded in your statement. Are we clear here?
Yeah. Good.
Yes.
Right. So that's number one. Number two, The way I have my components laid out, right? It is such that the first two columns after the condition column, right, is such that the components I have are the ones that are included in the first condition. In the first condition, the first make mention of the arm, hence the first column. The first column is going to be of the arm. Second column, the second component that make mention of here is the annulus. Hence, this represents the annulus. Right. I would insist that you take the very same approach. Makes things very easy. Right. Now, the columns that follow after the annulus, right, are based on how the gears are meshing, right? Meaning, I look at, so I have a column on the annulus. I then look at which gear meshes with the annulus. It is the planetary gear. So I have a column of the planetary gear. Then I look at which gear meshes with the planetary gear. It's the sun gear. Hence, I'll have the sun gear on this side. Are we clear here?
Can you just repeat that again, please?
So I said how I have my table laid out, right, is that the first two columns of my components, right, are going to be from what the components that are included in the first condition. In the first condition, you fix the arm. The arm is a component. That's why I have the arm here first. The second component that the first condition speaks of is what? The annulus. Hence, the second column of components is going to be the annulus. Right? The next columns are going to be based on how the gears are meshing. So by that, I mean, you have, what is this? You have the annulus. So next thing I look at is which gear meshes with the gear we are taking as our annulus. Right? So in this case, the gear meshing with the annulus is the planetary gear. Hence, next to the annulus, I'll have the gear that it is meshing with, which is the planetary gear. Next to the planetary gear, I'm going to have the gear that meshes with the planetary gear, which is the sun gear. Are we together now?
Yeah, definitely.
Right. So that is how I lay out my table. Right. I look at how the components or how the gears are meshing with each other. Right. That is going to be convenient again in what? In completing your first condition. Right.
Yeah.
Right. Now, let us write down the number of teeth of each of the gears. Right. In fact, first, let us write down our components. Right. If we look at the statement, they say an epicyclic gear train has a sun gear, koi, two planetary gears, the latter mentioned with the internal fixed annulus, right? The input shaft carrying the sun wheel is that, the output shaft is connected to an arm, right? So they didn't necessarily label the arm, they just called this an arm. So we are just going to call it the arm as well, right? So this will be the arm, right? The annulus hasn't necessarily been given a label as well. So we are going to call it gear A for annulus, right? So this represents gear A being the annulus, right? So this is the annulus. Same with the planetary gear, right? This we are going to label as P for planetary gear, right? And then this one is simply called the sun gear, right? So we're just gonna call it S for sun gear, right? And then this we do not have. Right? Right. Then once you have your labels right, what you do next is, right? What you do next is you write down the number of teeth of each of the gears, right? So we're going to look at the number of teeth of each of these gears, right? They said the sun gear has 20 teeth, right? And the planetary gear has 40 teeth. Do we see that here?
Yeah. Yeah.
Right. So the planetary gear has, so TP, right? For number of teeth, we denote number of teeth as small letter t, right? Always use small letter t, right? This is to differentiate between number of teeth and torque, right? By torque, this is what I'm referring to. Are we clear?
Yeah.
So this we would denote as capital letter T, number of teeth, small letter t, right? So TP, number of teeth of the planetary gear, is 40, number of teeth. For the sun, it's 20 teeth, right? Yes. So this is TS is equal to 20 teeth, right? It seems we haven't been given the number of teeth of the annulus, right? But now we know the approach to take in calculating the number of teeth of the annulus, right? We simply use this here, right? So using this, we'll simply calculate the number of teeth of the annulus. So essentially this will be equal to so this will be equal to 2 times TP. TP is 40. I hope you guys have your calculators there. Plus TS. TS is 20. And what do we get here?
100.
So this is 100 number of teeth. So the number of teeth of the annulus is 100. So here you write TA is equal to 100 number of teeth, right? So essentially, we have all the number of teeth of our gears. So it means we can complete condition 1. So this is what I meant by you have the number of teeth of all your gears, then that is all you need to complete condition 1. Are we clear here?
Yeah.
Right. Now let's look at how we complete the first condition, right? Out of all the conditions that you are going to have on the table, condition 1 is the most important. You mess up condition 1, it's pretty much over. Everything is contingent on you getting condition 1 correctly, right? So because of that, I've come up with these 3 steps in which you can use, right? In fact, in which I insist on you using to complete the first condition, right? You can write down the steps if you need to, right? And then if you can make a mental note, then you can do that as well, right? But it is important that you know the 3 steps you need to follow in completing the first condition, right? Once you get used to using the 3 steps, right, you won't have to write them down. You won't have to even think about them anymore, right? Now, as for the 3 steps, I hope people are listening here, right? So the first step is you establish the relationship between the 2 meshing gears, right? In fact, okay, wait, put a comma there, right? Put a comma there. I first want to explain what it is exactly that you are trying to accomplish in completing the first condition, right? We here?
Yeah, we hear you.
Right. So in completing the first condition, right, what we are trying to ascertain is the rotational frequency of the other components if the arm is fixed and the annulus has been rotated by 1 revolution clockwise, right? So essentially what we are trying to determine in the first condition is how would the arm being fixed and the annulus being rotated by 1 revolution clockwise influence the rotational frequency as well as direction of the other gears. So in this case, the planets as well as the sun gear. So the question you are answering in completing the first condition is, what is the rotational frequency as well as the direction thereof P and S if the arm is fixed and the annulus is being rotated or has been rotated by 1 revolution clockwise? right? So essentially, what you will determine here is the rotational frequency, right? There is this misconception that you are determining some ratio, right? So what you're determining here is the rotational frequency. We clear here. So by rotational frequency, I mean what you're trying to get here is NP. What is the rotational frequency and direction thereof? P, as well as, sorry?
Sorry, sir.
Right, as well as the rotational frequency as well as direction of S. So this is what you're trying to determine, right? Remember that the capital letter N stands for what? Stands for the rotational frequency, right? Stands for the rotational frequency. So you're trying to get the rotational frequency of the planets as well as the rotational frequency of the sun gear if the arm is fixed and the annulus has been rotated by 1 revolution clockwise. Are we clear? Hello?
Yes, sir.
Yeah, but I think I got lost now with the 3 steps.
Sorry?
That's already explained.
Say again?
The 3 steps, I'm kind of lost.
Oh, the 3
trying to
steps,
establish.
put a comma there. I haven't
Okay.
mentioned the 3 steps.
Oh, okay, all right.
Right. I first wanted to explain what exactly we are trying to determine in completing the first condition. Right. The 3 steps are only going to make sense if you understand this part. So do you understand what it is that you are trying to determine here?
Yeah, no, I understand that.
All right. Now, as far as the 3 steps, right? There's 3 steps you need to follow in completing the first condition, right? First step is the relationship, right? You first have to establish a relationship or the relationship between the two meshing gears. So by that, I mean, we want to complete the first condition under this column, right? This column is for the planetary gear. So you look at which gear meshes with the planetary gear, right? In doing that, you look at the column that comes before it. The gear that meshes with the planetary gear is gear A. Well, it is also gear S, but you don't necessarily have any information here, right? Hence, we are going to use the annulus. So in establishing the relationship between the two meshing gears, right? To get this one, you would then look at the relationship between the planetary gear and the annulus, right? Establish the relationship between the two gears. That's the first one. Second one is establish direction of rotation. Third one is you solve for what you're looking for, right? So let us first establish the relationship between the planetary gear and the annulus, which are the two meshing gears. Now, how do you establish relationship, right? If you have a gear, right, and this gear is meshing with another one, right? So this is just in a general perspective, right? Say this is gear A, that's gear B, right? Gear A is rotating clockwise, so meaning this one is rotating anti-clockwise, right? When you establish a relationship between two meshing gears, right, the two meshing gears are only going to have one relationship, and that relationship is going to be one of circumferential velocity, right? Where the gears meet, right? So at that point, where the gears meet, right, they have what we call a circumferential velocity, right? So there you have the circumferential velocity, right? Circumferential velocity, also known as tangential velocity, right? The circumferential velocity, right, is linear, and it must be in a direction that corresponds to how the gears are rotating, right? So if this one is going clockwise and this one is going anti-clockwise, if looking at this from a linear perspective, right, the direction will be downward. Can we see that?
Yes, sir.
Right. So the relationship between two meshing gears is one of circumferential velocity, right? So meaning the circumferential velocity, so this is circumferential velocity. Velocity, right? Also known as the tangential, right? This is going to come in handy when you guys do Mechanotechnics N6, tangential velocity, right? Now this in general is equal to what? Pi dn, right? So when we say the relationship between the two gears is one of circumferential velocity, we mean that for meshing gears, their circumferential velocity is the same. So meaning VA is equal to VB. That is the relationship between the two gears. Are we clear here? Hello?
Yes, yes,
Yes, sir.
Yes, sir. Right. So first step, establish the relationship between the two gears. That relationship will always be one of circumferential velocity. The circumferential velocity of two meshing gears is always the same, right?
Okay.
Now, bearing in mind that the general formula for circumferential velocity is pi dn, right? For gears, we do not necessarily use diameter, but we use PCD, right? For gears, we instead use pi times PCD times the rotational frequency of the gear, right? So if VA is equal to VB, it means that essentially, what is this? Pi times the PCD of A times the rotational frequency of A is equal to pi times the PCD of B times the rotational frequency of B, right? And then pi being the same on either side is going to cancel, right? And then we are able to express the PCD in terms of its formula. Remember that PCD is equal to module times number of teeth. So we say module times the number of teeth of A, right? This here is what is equal to the PCD, right? Multiply this by the rotational frequency of A. This is equal to, we do the same thing on this side, module times number of teeth of B times the rotational frequency of B, right? Again, if gears are meshing, it means their modules are the same. So mathematically, this and this cancels. So essentially, you are left with NA times TA is equal to NB times TB, right? So by establishing the relationship between two gears, this here is what we mean. The relationship between A and B is one of circumferential velocity. That means that NATA is equal to NBTB. This here is the relationship between the two gears in mesh. Right? So this is the relationship between the two gears. So this is what I mean by first thing you do is establish the relationship between the two meshing gears. Are we clear here?
Yeah.
So that means you do not necessarily have to do all of this because mathematically we know now it is going to work out to be equal to that. Right? So when I say first step is establish the relationship between the two gears, this is the relationship between the two gears. If two gears are meshing, right, the rotational frequency of the product of the rotational frequency of the one gear and its number of teeth is equal to the product of the rotational frequency of the other gear as well as its number of teeth. Are we clear? Right? Now, once you've established once you've established the relationship between the two gears, right? So this is first step. Once you've established the relationship between the two gears, you now establish direction of rotation, right? So we look at how is this gear rotating and how is this gear rotating, right? Now, considering this typical case, we said this is going clockwise, right? So it means the direction of A is clockwise. So because it's clockwise, you're going to leave it as positive. And then we're looking at B. Because A and B are rotating or are meshing with the outside true circumference, they go in different directions, right? So if this is going clockwise, that's going anti-clockwise. So because B is going anti-clockwise, right, you then insert a negative sign there. Are we together?
Yes, sir.
Yes, sir.
Right, so this is the second step. So first step, establish the relationship between the two gears. Second step is establish direction of rotation, which we just did. So this would be the second step, right? Third step is you solve for what you're looking for, right? Say in this case, we are looking for NB, right? So because you're looking for NB, what you would then do is solving for NB, right? Remember you have NA times TA is equal to negative NB times TB. If you're looking for NB, so solving for NB or making NB the subject of the formula, you would then have to divide both sides by negative TB. Obviously, this cancels. Therefore, meaning solving for what you're looking for, which is NB, NB is equal to this here. NB is equal to NATA divided by negative TB, right? And then this is what you would insert in your what? In your first condition. Right, so this here being, what is this thing? So this would be your third step, solving for what you are looking for. Right, so this is third step. Right, so first step is establish relationship between the two meshing gears. Second, establish direction of rotation. Third, solve for what you're looking for. Three very easy steps. Are we clear? Hello?
Yes.
Are we clear?
Yeah.
Yes.
So for now, you used it in a very simple explanation. Can you take it to the example that you had on top now?
That's exactly what we're going to do now.
Okay.
Right, I just wanted to explain the three steps, right, using a very simple example, just looking at two gears. Right, so now we are going to apply this, right, on this exercise. But are people now aware of the three steps? Do they understand how the three steps work?
Yeah.
Right, now let's apply the three steps on this exercise, right? We want to determine NP and NS. So first with NP, right? Which gear is NP meshing with? It is meshing with the analyst, right?
Yes.
Right.
Mm-hmm.
Now we look at the relationship between the two gears. So the relationship between NP and NA. The relationship between NP and NA, right, is one of circumferential velocity, right? That means NP times TP is equal to what? NA times TA. You've established the relationship between the two gears, right? Next, you establish direction of rotation, right? Now we are looking at a typical epicyclic gear, right? Whichever gear that meshes with the annulus, right? If the annulus is such that it has teeth ground onto it on the inside through circumference, right? Whichever gear that meshes with the annulus with those teeth tends to go in the same direction as the annulus, right? Now the annulus here, from the first condition, we're told the annulus must rotate by 1 revolution clockwise. So we know that the annulus is rotating clockwise. So if the annulus is rotating clockwise, what does that tell us for the planetary gear? Bearing in mind, exactly, yes, going clockwise as well, right? So we've established the relationship between the planetary and the annulus. Next, you establish direction of rotation. We know the annulus is going clockwise, right, from the first condition, so this remains positive. Now, the planetary gear, as we've established, is also going clockwise, so you leave it also as positive, right? So third step is solve what you're looking for. We're looking for NP. Therefore, you divide both sides by what? By TP. Divide both sides by TP, divide by TP. That goes, meaning NP is equal to NA times TA divided by TP, right? So to get NP, NP is equal to this. Right? Now you simply substitute. What is NA equal to? NA is the rotational frequency. Sorry?
What?
There we go. Right? Remember, you were told that the annulus is rotating by 1 revolution clockwise. So NA is 1. So this is 1 times TA. TA we calculated and got 100. So that's 100 divided by TP. TP is 40. Right? And what do we get here? What is 100 divided by 40?
2.5.
Okay.
Calculators, people.
It's 2.5.
So this is 2,5. Right? See how easy that was? Right? Now we do the same thing with gear S. Right? We're going to do the same thing with gear S. Right? Which gear is gear S meshing with? It is meshing with the annulus. Right?
No.
So,
No, with the planet.
Oh,
not the annulus, the planets are the gear. Very good there, by the way. Yes, you're right. It is meshing with the planetary gear. Right? Now, what is the relationship between the two gears? The relationship is that NS times TS is equal to NP times TP. That's the relationship between the two gears. Second step is direction of rotation, right? We know NP is going in which direction?
Clockwise.
Going clockwise. Now,
Yeah.
you have to bear in mind that the planetary gear and sun gear are meshing with the outside through circumference. Meaning what is phi's direction? Are they going to go in the same direction or opposite directions?
Opposite.
Opposite.
Right. So if this is going clockwise, how is this rotating?
Anti-clockwise.
Right. So that is negative. Right. You've established direction of rotation. Now for the third step, solve what you're looking for. We're looking for NS. So we divide both sides by negative TS. Obviously that goes, and NS is equal to NP times TP divided by negative TS. All right, so to get NS, this is what we are looking for. All right, NS is equal to this here. Now, all you do is simply substitute, right? Now, what is NP equal to? NP is equal to 2,5, right? So this is 2,5 times TP. TP is 40. All of this divided by negative TS. TS is 20. And what do we get here?
5.
Sorry?
-5.
Negative 5, yes. So negative 5. And that's how you would complete the first condition, by using those 3 very simple steps. You use those 3 steps, you will never go wrong with the first condition. Are we clear here?
Yes, sir.
Right? Beautiful. Now, another thing, you must always make sure that that direction here, right? That direction you get is always aligns with how you assumed that this is rotating. Right? You established that this is going clockwise, hence this also has to be positive, corresponding with the direction you assumed initially. Similarly with the gear S. Zonke, please turn off your mic. Right? Similarly with gear S, right? With gear S, we assume that seeing that these two are meshing with the outside true circumference, if this is going clockwise, this is going anti-clockwise, right? So that assumption, right, must remain true in whatever you get here. So seeing that this is negative, right, the negative sign corresponds with how this is rotating, right? So just be wary of that. Just in case you happen to forget the negative, right? Always make sure that the direction of this gear corresponds with what you calculated as far as the direction. We good?
Yeah, no, we're good. So will there be a case whereby the like you said, the contact is on the outside of the gear? Will there be a case where the contact is on the inside?
Second?
You're saying the direction will change because the gears are meshing on the outside, right? Will there be a case where you have your gears meshing, like for an example, with the example you have here, where your analysis is actually not fixed? So that will obviously impact your T, right?
Yeah.
Yeah. Will there be a case whereby your S will be like positive? That's what I'm trying to say.
There's no way.
There's
As
no
long
way.
as there's absolutely no way. As long as you are looking at a typical epicyclic gear system, a typical epicyclic gear system, the annulus measures the planetary measures with the sun, right? So seeing that the annulus is going to be our annulus. If this is rotating clockwise, this will always rotate clockwise, and this
Right.
will rotate anti-clockwise. That will just always be the case.
Yeah.
Right?
Okay.
It's only when we get to say the third condition, right? In the third condition, right, we have to apply what has been said in the statement and the question you are looking at, right?
Yeah.
But as far as the first condition, this will always be the case for a typical epicyclic gear system, right? Because taking this as our annulus will always be going clockwise. If this is going clockwise, that's definitely going clockwise. If this is going clockwise, this is definitely going anti-clockwise. So for the first condition, when looking at a typical epicyclic gear system, this, as far as direction, will always be the case. Light?
Question, sir.
Sure.
If there were 3 planetary gears, they all would have the same rotational frequency.
Yes.
Okay, thank you.
That is why it doesn't matter how many planetary gears there are here. There could be 8, there could be 10, there could be 100. It doesn't matter.
Yes, that's why you only use one P,
Just
and you
one.
don't have P1 in the. Thank you,
Yes.
sir.
Any more questions? No questions. Wonderful. Right. So to complete the first condition, you only need the number of teeth. If you have those, then you only need to use those 3 steps to complete the first condition. Establish the relationship between the 2 meshing gears. Establish direction of rotation. Solve what you're looking for. 3 very easy steps. Are we clear on the steps here?
Yes.
Sir, yes, sir.
Right. So once the first condition is complete, you then complete the second condition. Like I said, the first condition is the most important condition here, right? To complete the second condition, you must have completed the first. In completing the second, right, second condition is you multiply the first condition by x, and then you add y, right? So essentially, we're going to say x times 0, that's 0, plus y is just y. X times 1 is x, then you add y, so plus y, right? Then x times 2, 5 is 2, 5x, then you add y, so plus y. Negative 5 times x is negative 5x, then you add y, so plus y. Right? And second condition is complete. Are we clear here?
Can you just repeat it for me once more, please?
Yes, sir.
Right. So what I said was once the first condition is complete, your second condition is you must multiply the first condition by x. So when you say multiply by x, it means multiply the first condition by x, right? And add y. So multiplying the first condition by x, you're going to say x, for instance, for this column for the arm, it's going to be x times 0, which is 0. And then you add y. So this will only be equal to y. Right? And then for this one, multiplying this by x is going to give us x. Then you add y. Right? And then multiplying this by x gives us 2,5x. Then you add y. Multiplying the first condition by x gives us negative 5x. Then you add y. That's what we mean by the second condition. We good?
Good.
Right? So first and second condition are complete. If you noticed, we haven't even read the statement. We haven't even read the questions. Why? Because we're able to identify the number of teeth. So for the first condition, all you need is your number of teeth to complete the first condition. Are we clear here?
Yep.
Yes, sir.
Yes.
Right. So seeing that the first and second condition are complete, we then look at what we have in our statements and what the question is asking for, right? Now, before we do that, let me just make mention of this, right? Every condition that follows after the second condition, right? Every condition that follows after the second condition, right? To complete that condition, we are going to need three things, right? So every condition that follows after this, for us to complete that condition, we are going to need three things. We are going to need what you are looking for, number one, and two other assumptions, right? So meaning now we are going to have a third condition. For us to complete the third condition, we are going to need what we are looking for and two other assumptions, right? Now, what you are looking for, you are going to get from the question, right? But as far as the two assumptions, right? The two assumptions can be given to you in the question, or both assumptions can be embedded in the statement, right? That is why it is important to go through the statement when having to look at the conditions that follow after the second condition, right? Right. So first, looking at the question, calculate the speed of the output. So that is what we are looking for. So we have one of the three things we need to complete the third condition. Now we need two assumptions to complete the condition, right? We have to calculate the speed of the output shaft, right? So now we go back to the statement. An epicyclic gear train has a sun gear wheel with 20 teeth and two planetary wheels of 40 teeth each, the latter meshing with the internal teeth of a fixed annulus, right? So the annulus is fixed. That's one of the assumptions. Right? The annulus being fixed means that it is not rotating. So meaning that NA, which is the rotational frequency of the annulus, seeing that the annulus is fixed, this will be equal to 0. Are we clear here? Are we in agreement here?
Yes.
Right? The input shaft carrying the sun wheel, right? The input shaft carrying the sun wheel. So essentially the input shaft is fitted onto the sun gear. So meaning that whatever the rotational frequency is of the shaft, right, the sun will be rotating at the very same frequency. Wheel transmits 4 kilowatts at 300 revs per minute, right? So if the input shaft is rotating at 300 revs per minute, it means the sun gear is also rotating at 300 revs per minute, seeing that the input shaft is carrying the sun gear, right?
To say that again, sir?
So the statement says the input shaft carrying the sun wheel, right? So essentially what that means is that the input shaft has been fitted onto the what? Onto the sun wheel or the sun gear, right? Transmits 4 kilowatts at what? At 300 revs per minute. So if the input shaft is rotating at 300 revs per minute, it means the sun gear is also rotating at 300 revs per minute. Why? Because the input shaft has been fitted onto the what? Onto the sun gear.
Thank you, sir.
Are we in agreement here?
Correct.
Right. So our second assumption essentially is that the sun gear is rotating at 300 revs per minute. They didn't indicate if that is clockwise or anti-clockwise, but because this is positive, we are going to take it as clockwise. So the second assumption essentially is NS, right, which stands for the rotational frequency of the sun gear is positive 300. Are we clear here?
Yes.
Right? So we already have two of the assumptions. Now we need what you are looking for. And we are going to get that in knowing where the output shaft, which component the output shaft has been fitted on. They say the output shaft is connected to an arm that carries the planetary wheels. Right? The output shaft is connected to the arm, right? So essentially, when they say calculate the speed of the output shaft, right? Essentially, they want us to calculate the rotational frequency of the arm, seeing that the output shaft is fitted onto the arm. So essentially, what we are looking for is the rotational frequency of the arm, right? If you get the rotational frequency of the arm, you inadvertently get the rotational frequency of the output shaft, right? So here we are looking for the rotational frequency of the arm. So that's what you're looking for, right? NA is equal to 0. They said absolutely nothing about the planetary gear. And this is the sun gears rotating at positive 300, right? Remember what I said? To complete the third condition, you need three things: what you're looking for and two other assumptions, right? So our third condition is now complete. Right? Any questions? No questions. Wonderful. Now, to determine the rotational frequency of the arm, right? What we do next is we are going to equate the third condition with the second condition to what? To formulate equations, which will then solve simultaneously to determine what we are looking for, right? So to get what we are looking for, you have to formulate equations. And the way you formulate equations is by equating your third condition with your what? With your second condition. So doing that, you have y being equal to what? Being equal to n arm. So this you take as your first equation. Second equation will be you equate your second and your third condition. So this will be x plus y is equal to 0. This you take as your second equation. To get your third equation, you then equate this second condition to this third condition. So you have minus 5x plus y is equal to positive 300. This becomes your third equation, right? So now you formulated your equations. Now looking at what exactly we're looking for n arm. In order to get n arm, you need to get the value of y, right? So to get the value of y, we simply need to solve these two simultaneously, right? The easiest way of doing that for this case would be to express x in terms of y, right? Once we've expressed x in terms of y, from this equation, right, we'll only have one unknown. So by that I mean you take equation 2 and you express x in terms of y. So you're going to transpose this to that side, and you're going to be left with x is equal to negative y. So this becomes your fourth equation, right? Now you take your fourth equation and substitute it into the third equation, right? Right. I want to add, right. Right. So we are going to substitute. We are going to substitute, right? Substitute the fourth equation into the third equation, right? By the way, at this, right, at this point, Meccano is finished, right? Meccano ended when we completed our third condition, right? All this is now is just maths, right? So substituting the fourth into the third equation, we are going to have negative 5x. X from the fourth condition is expressed in terms of y, and it is equal to negative y plus y is equal to 300, right? And then, as you know, multiplying these will give you a positive, right? Positive 5y plus y is 6y. So this becomes 6y is equal to 300. Then to get the value of y, you simply divide both sides by 6, right? That cancels. Therefore, meaning y is equal to what? What is 300?
50.
50.
This is 50. So the value of y is equal to 50, right? Now to get the arm, we know n arm is equal to y. So you simply say, therefore n arm is equal to y, which is 50. Right, so seeing that this is positive, right, it means this is 50 revs per minute, right? Because it's positive, it means it's going clockwise. So you indicate the direction as well, right? If y had been negative, so if y was equal to negative 50, it means n arm, right, would have been equal to what? Y, which is negative 50, right? This means that the n arm is equal to 50 revs per minute anti-clockwise. Very important to indicate the direction, right? This is an indication of how the arm is rotating. Are we clear here? So you do not leave your answers as just negative or positive. You have to indicate what either positive or negative means. Are we clear here?
Yeah.
Yes, sir.
Yes. Yes. Oh, there was a yes. Okay. So this was hypothetical, so I can remove this. Right? So because y is positive, right, you then show that by indicating the direction. CW stands for clockwise. Any questions? Any questions?
Nope.
All right, no questions. Wonderful. Right, this is where we are going to end our session. All right, seeing that there are no questions. Right, this is where we are going to end this session. Right, it has gone way beyond what it was supposed to be anyway. Right, so now what you guys are going to do is I will be sending what we covered today. So I'll send what we did today in the group, right? And I'll be uploading this session on my channel, my YouTube channel, right? So if you need to refer to the lesson, you can go to the channel, right? You'll get the video there. I'll also be sending you past exam questions, right? which you can use for practice under Epicyclic Gears. Right, and then if you have questions, I'll be available on the group as well, right?
Meneer,
Yes.
when are we going to have?
Sorry?
When are we going to have another class?
Another class, I will update you on that. It might be Sunday, it might be Monday, but as from next week, we are going to have possibly 2 sessions a week.
Okay, can you please, when we have class, can you please update us in time, because
Accept you in time.
today, update.
Or update. Oh, no, don't worry about that.
Thank you.
As I'm saying, as from next week, you will know exactly the days in which we'll have sessions, right?
Okay, thank you, sir.
I want to try and offer as much guidance as possible, right? We are, on paper, we are supposed to give you 11 sessions, right? 11 sessions, though, for engineering is not practical, right? So that's why I try to go above and beyond for you guys, right? So I will try to make it so that we have 2 sessions a week, right? But 1 session definitely we are going to have a week. Are we clear?
All right. Yeah.
Right. As to which days our sessions are going to be, I will update you on that one. As far and as well as the time. Right. For now, though, you have enough to continue doing problems on what is this? Epicyclic gears.
Epicyclic.
Right. And then if you have questions, I'm available to answer questions in the group.
Okay. Thank you very much.
All right. If there is
Thank you,
nothing,
sir.
sure. If there's nothing further, we can end the lesson here.
Thank you. Bye-bye.
All right. Thank you.
Cheers, Chief.
Thank you, sir.